When a high-speed driven shaft violently sheds its components, the failure rarely starts with a shattered gear or a cracked housing. It begins with an unconstrained fraction of a millimeter. The clearances and threads required for assembly are the same pathways that vibration and load use to dismantle the system. The tolerances that permit a technician to build a machine are exactly what allow mechanical forces to tear it apart. Building a reliable assembly requires engineers to intentionally arrest specific degrees of freedom without permanently welding the parts together. They must counteract three distinct threats: vibrational loosening, rotational shear, and axial sliding. Reliability depends on deploying exact geometries to block these forces, rather than relying on raw torque. Look at a bare threaded shaft. Under heavy vibrational loads, a standard hex nut will naturally backdrive down the threads. The continuous shaking acts as a tiny, rapid untorquing sequence. The first strategy to arrest this backdrive is friction locking, achieved using a check nut, often called a jam nut. A check nut is exactly 2/3 the thickness of a standard nut, with both faces machined flat. Placed below the primary nut and tightened in opposite directions, it binds the internal threads tightly against the bolt, creating a severe friction lock. When manual double nutting isn't practical, we use deformation locking. The most common iteration is the Simmons lock nut. At the top of this nut sits a captive ring made of nylon or fiber. This nylon ring lacks pre-cut threads. The inner diameter is sized slightly smaller than the bolt itself. As you drive the bolt upward, the metal threads physically cut their own path into the nylon, generating intense radial friction that stops vibration dead. Then there's geometric pinching, a method utilized by the swan nut, sometimes referred to as the Wiles nut. The swan nut has a lateral slot cut halfway through its solid body. A small set screw spans this gap. When the set screw is tightened, it physically pinches the two halves of the nut together, clamping the internal threads directly onto the bolt. For absolute security, we abandon friction entirely and use positive locking methods. Here you have two options: the slotted nut and the castle nut. A slotted nut has cuts milled directly into its hexagonal faces, which structurally weakens the tightening surface. A castle nut solves this by adding a distinct cylindrical collar on top, specifically to house those slots. Regardless of the type, both of these nuts function the exact same way. A split pin is passed through the slots and a hole cross-drilled in the bolt, creating a physical barricade that cannot rotate under any amount of vibration. Arresting vibration always comes down to the same principle: forcing a rigid, opposing geometry against the natural backdrive path of the thread. Moving down to the base of the fastener, we have to correct a widespread professional misconception regarding plane washers. Plane washers do not lock assemblies. They provide no rotational resistance. Their sole mechanical purpose is expanding the pressure-bearing surface area to prevent the bolt head from crushing the material beneath it. They are governed by a strict dimensional formula. The outer diameter is equal to 2 times the bolt diameter, plus 3 millimeters. The required thickness is precisely 0.125 times the bolt diameter. If active locking is required at the base, you must pivot away from plane washers entirely. Instead, you deploy spring washers, which use stored spring tension to prevent loosening, or toothed washers, which physically bite into the bearing metal. For extreme rotational constraint at the base, you use tab washers, where a metal tab is bent tightly against the physical edge of a component, or lug washers, featuring a specialized tab that is driven down into a pre-drilled hole in the bearing surface. In mechanical design, there is a hard line between a passive load distributor and an active physical stop. Washers are no exception. When we move away from threaded fasteners and look at smooth, driven shafts, the mechanical demands flip. A gear must have the freedom to rotate with the shaft, but if it can uncontrollably slide left and right, the transmission will fail. The precise geometric solution to arrest this lateral sliding is the circlip, also known as a snap ring. Circlips are classified by their directional tension. Internal circlips are compressed to fit inside a cylindrical bore, snapping outward to lock. External circlips are expanded to fit over a shaft, snapping inward into a machined groove. Because they are forged from high-tension spring steel or stainless steel, installing them safely requires specialized long-nose pliers. Once seated, a circlip acts as a perfect axial border. It completely limits sliding movement on the z-axis without inducing any friction against the rotational path. Keys solve the exact inverse problem of the circlip. They arrest rotational slip, forcing a gear and a shaft to spin as a single unit, while technically permitting the gear to slide axially. To understand keys, you have to use correct terminology. The channel cut into the interior of the hub is called the keyway. The matching channel cut into the outer surface of the shaft is the key seat. For light load transmission, we use the saddle key. A hollow saddle key has a curved bottom sitting directly against the smooth shaft's outer circumference. It relies entirely on friction to transmit rotation, meaning the shaft requires no key seat at all. For heavy loads, friction will fail. You must use a sunk key. This requires matching slots cut into both components. The sunk key mechanically interlocks the hub and shaft, absorbing massive rotational shear forces directly into its steel flanks. When working with tapered shafts or slight mechanical misalignments, engineers use the Woodruff key. Its semicircular half-moon geometry allows it to tilt inside a deep, curved key seat, aligning itself perfectly with the hub. If a key will need to be extracted repeatedly from a heavy assembly, the gib head key is deployed. It features a 1:100 taper and a raised 45-degree head that allows technicians to wedge a tool underneath it for rapid removal. If a hub needs to slide axially back and forth while continuing to transmit rotation, you use a feather key. A specific variant, the peg feather key, achieves this using a central cylindrical peg that drops directly into a hole drilled in the hub. Finally, for extreme bidirectional shock loads, like those found in rolling mills or heavy flywheels, engineers use tangent keys, installing two separate keys driven in at 120-degree angles to each other. Selecting a key is never a random choice. It is dictated entirely by the magnitude of the load and the direction of rotational shear stress. When you look at the broad spectrum of industrial hardware on a finished machine, the sheer number of fasteners and retainers can look overwhelming, but trace every component back to its origin and you find a calculated geometric answer. Jam nuts and nylon rings counter friction. Circlips halt axial slip. Sunk keys absorb shearing force. Mechanical stability is an illusion. A working machine is just the highly calculated limitation of movement across very specific axes. Mastering these specific forces and formulas transforms an assembly from a collection of parts into a precisely managed system of vectors and constraints.